Hey, D-Heart, Caleb here.
You might find the sound of a CRT a bit annoying, but with modern technology, we can target and remove ambient sounds. We could remove the sound of the CRT, the fountain behind the camera, and even the rustling leaves. But how does this work? It would be like unmixing mixed paint.
In the example of paint, you have multiple colors combined together to create a new color. For example, the color orange is a mixture of the colors red and yellow. Any color you see is a combination of many different primary colors. In the same way, any sound you hear is a combination of many different frequencies, all added together. This is not your standard wave, but as it turns out, it can still be represented by a simple combination of these two sine and cosine waves. Using periodic functions to represent sound is called a Fourier series. Actually, you can represent any graph with a Fourier series. Take, for example, my good friend Homer Simpson.
After we convert sound into a Fourier series, we can take out the frequencies we don't want and combine the rest back together. It would be like unmixing paint, taking out the colors we don't want, and mixing the rest back together to create a new color. The problem is, we don't know how to convert sound into a Fourier series. We want something that operates like a prism. A prism scatters light into the colors that make it up. We need to do the same for sound.
The Fourier transform is actually how you turn any graph of values into a Fourier series.
This equation might seem intimidating. When you look at it, you might feel something like this.
Caleb, don't worry about it. This is simple. Look beyond the math.
When you look past just the math, the concepts really are fairly simple. Say you have this graph. It looks completely random and extremely difficult to decipher. However, it is only made of 5 cosine graphs summed together. When we superimpose the gray graph, which is one of those 5 cosine graphs, you can see that the frequency lines up really well with a lot of the peaks and troughs found in the original graph. This is, in essence, what the Fourier transform does. It scans through every single possible frequency and finds out how well it lines up to the original graph's peaks and troughs. Each of these frequencies it scans through will be given a value depending upon how well it correlates with the original graph. The better a frequency lines up, the greater the value will be. If it does not line up very well, then the value will be very low. For example, this frequency would have a low value, and this frequency would have a high value. You can then take all of those values and make a graph, where at the x-axis is the frequency, and the y-axis is the value that we assigned. So, in short, we took a graph of time to energy, which is sound, and converted it to a graph of frequency to this value that we are creating. Here's what the actual output of the Fourier transform would look like. On the left, we have the original sound, and in the middle, there are the frequencies that make it up. On the right, we have a graph of the Fourier transform. The 3 peaks correlate with the 3 frequencies that actually make up the original sound that you can see in the middle. All of the other frequencies have a very low value, and thus do not correlate with the original sound very well. This might be best seen by actually seeing the Fourier transform real time. Here, I have my microphone connected to my laptop, and this program is showing the microphone input on the top graph, and the Fourier transform of the microphone in the bottom graph. As you can see, my normal talking voice is almost like white noise, or made up of many different frequencies, and not dominated by any one in particular. If I whistle, however, a single frequency comes out. As you can see, the graph had a large spike as I whistled, because it can easily find the frequency of my whistle. Of course, it can also pick apart multiple frequencies being played at once. Here, I have a recording of me playing a few notes on my guitar. As you saw, the graph had two spikes as I played the notes together.
In wave mechanics problems, we're usually asked to find information about the graph of a wave in simple harmonic motion. In the real world, there's no such thing as simple harmonic motion. With the ability to compute the Fourier transform, we can face much more realistic problems while still using the same basic principles. We can break down even the most complex periodic movements into sine and cosine waves and work with them much like a Physics 1 problem.
For a physical example of this, let's suppose we have two springs of different stiffness connected together. Objects of different weight are connected to the end of each spring. The position graph of the object, even if both springs were in true simple harmonic motion, would be very hard to analyze. If we took that graph and applied the Fourier transform, we could actually decompose the graph into the periodic functions that we're used to and analyze the movement much more effectively.
The use cases of the Fourier transform span many different fields, and even impact your everyday life. One important use case of the Fourier transform is in data compression. When a computer compresses a file, it is attempting to reduce the amount of data in a file while still retaining all of the important information. The Fourier transform can be used to separate out unnecessary or unimportant frequencies and delete them, so that the data can be less complex while maintaining nearly all of the original information. This is used in audio formats that we use every day, like the MP3. Even doctors use a Fourier transform. Even though MRI images may not seem periodic, you can still run the Fourier transform on them. This process is very abstract, and well outside of the scope of this project. However, even though it is outside of the scope of this project, it is a great testament into the many ways that the Fourier transform can be used. Here you can see an MRI scan on the right, and its Fourier transform on the left. Using the transform, doctors can manipulate the image in various ways that allows for them to analyze the image more easily. Using the transform, they can remove artifacts, producing a clearer image. Additionally, they can produce an MRI with just the edges of the scan, which allows them a clearer view into the image. The possibilities go beyond math and physics. The Fourier transform is extremely relevant, even for a non-mathematician. We haven't even mentioned the possibilities of using it for signal processing or for optics.
So, to go back to the introduction, the way we removed background noises was a very simple process. We ran the Fourier transform on the sound, and found the frequencies of both the fountain and the CRT. Once we found the background noises, we removed them and recreated the sound.
And all that remains is my beautiful, beautiful voice. Remember to stay curious, and as always, thanks for watching.